I'd like to explain two of the relatively hard questions in quiz 1, based on the feedback and my experience before in previous semesters. These two questions relatively hard. So let's look at the first one. Question number 4. Given a computing problem, if you have an algorithm to solve it and you cannot improve it anymore, then you can say that your algorithms is optimal. The answer is false. Why? Some of you missed these questions. So you may like to know the answer. So here, let me explain why it is false. All right. So this question, for many students, if you answer based on your intuition, it is very likely you select the false answer, intuition. Because, by your natural understanding, you cannot improve it anymore, then it must be optimal, right? But that is based on some weak logic, not strong, solid logic. Why is that? First, let's look at this U. The meaning of this U. How should we understand the U here? All right, So is it a literal U? Literal U, that is the student yourself, the literal you, or a general you, so not necessarily individual student, just some general, ordinary person, we can consider that person who answers this question. So actually here, we can treat as the general case. All right, but some of you may argue I treat as literal. Actually, for literal case, it will be easier to answer, right? Much easier to answer this question, because if it's a literal you cannot improve, but some other student, smarter, stronger, more experienced, some other people can improve it, right? So in that understanding, it is easier. So for literal you, it is much easier. Okay, so it is false, because you can find a much stronger problem solver to improve this algorithm, right? All right, so here, let us get to this general case. All right, so you can pick a representative here. All right, how about we pick the strongest problem solver on the earth. How about that? Strongest problem solver on the earth. How about that? Is it fair? Yeah, it is fair, right? We just imagine there is such a person we can find to answer this question. Then, if you still under that assumption, you answer this question, can you say it is true? Yep, because nobody is better than this guy, right? Even that, the answer is still false, right? Strongest problem solver on the earth, that's at the current time, right? Think about that. That's at the current time, okay? Not future time. How about that? Not future time, right? Yep. Even the smartest person on earth at current time cannot solve it. How do you know in the future, after 3 or 4 generations, there is a much stronger, much smarter problem solver who can improve this algorithm? How do you know that, right? Yeah, so even that, the answer is still false. Because you may know there is a famous problem, it's called a Fermat's last theorem. Fermat's last theorem. Very famous problem. It was solved in about 1995. Okay. It lasted more than 300 years. After more than 300 years, it was solved. It took human more than 300 years to solve this problem. That means, you know, some problems the current generation cannot solve. Then after several generations, then it is possible some smarter or some problem solver with much more advanced knowledge who can solve it, right? Yeah. So even under that assumption, this answer is still false because, yeah. So that kind of background, yeah, that makes, you know, this question a little tricky. Yeah. But if I say in this way, then another natural question after that. Yeah, so here, some natural question after that. Based on that understanding, it looks like all computing problems, it looks like all computing problems are not optimal. Yeah, so here or I just say, I like this one, may not be optimal. Or, yeah, let me write stronger, are not optimal. If you use, future generation argument, because, you don't know in future generation, there is some stronger problem solver who can solve it. You use the same argument, but answer is no. Yeah. For that question, answer is no. Why? Because we have an example. In this class, we proved we did one example. Yeah. We have that. What example tell us we solved a computing problem with optimal solution. What is that? That simple problem, quite useful here. It's a good example here. You can argue against the above question. Yeah. So that is in our module 1. We have that question. Yeah. Finding the minimum problem. Finding the minimum problem. All right. Okay. Yeah. And we proved it is optimal. All right. So remember, the answer is we use n-1 comparisons to find a solution. We proved nobody can solve this problem with fewer comparisons. That means n-2 comparisons. Nobody can find the minimum with n-2 comparisons. Okay, yeah. This one, there is no uncertainty. Okay, so even in the future generations, no matter how smart, how stronger that particular problem solver is, nobody can do it with n-2 comparisons. How about that example? Right? It is optimal. We can comfortably say it is optimal. How about that? Okay. All right. So you can see, to answer this question, you need a lot of background. The good thing is we learn it in this class, right? The background you need, we have learned in this class. Okay. Yeah. Finding the minimum. Yeah. That one. Yeah. We learn it. Okay. Yeah. So you can understand the answer from all these aspects, then you should feel very comfortable. Yeah. All right. Let me move to the next question. Yeah, it took me quite some time. Yeah, let me move to question number 7. Yeah, this one, yeah, quite challenging. Yeah. A few students asked me about this one. Yeah. The answer is 3. Yeah. But many of you give the answer 5 based on honors rule. Honors rule. Yeah. Because the highest degree 6 minus 1, that is 5. Right? Yeah. So you only use part of the knowledge we have learned. That is honors rule. Part of the knowledge. Okay. But there is another part you may forget. Yeah. Because look at the special coefficients. Here, the coefficients I give you quite special. It's not arbitrary. Arbitrary. There is a pattern. Look at the pattern is important. Yeah. All right. Yeah. So the pattern actually give us the structure of the sequence of coefficients that follows the structure, so-called Pascal's triangle. Pascal's triangle. All right. I talk about this property in one of our lectures. Yeah. Some of you may forget it. Yes. Yeah. Pascal's triangle. All right. Yeah. That is 1, 1, 1, 1, 2, 1. All right. Yeah. Because that corresponds to a plus b to the nth power. Binomial formula. If you do the expansion, the coefficients you have follows the Pascal's triangle. All right. 1, 4. The 4 comes from 1 plus 3. 3 plus 3, 6. 3 plus 1, 4. Then 1 here. All right. Then next level, yeah, another level, 1, 5, yeah, 10, 10, 5, 1. All right. Then the last one, that's our given coefficients. 1 here, 6, 15, all right, 20, 15, 6, 1, and it corresponds to that a plus b to the 6th power. Okay, yeah, 6, because this 6 tell us the exponent number. And for our current question, our a and a b, a is 1, b is x, 1 plus x to the 6th power. All right, to calculate 1 plus x parenthesis to the 6th power, how many multiplications do you need? Right? This time it's quite different, because we do not count addition, we only count multiplication. Yeah. Here, you can use repeated squaring technique, right? Repeated squaring technique here. Oh, all right, sorry, yeah, squaring technique. All right, yeah, 1 plus x, 6. So 1 plus x times 1 plus x. All right, that's the first multiplication. 1 plus x squared times 1 plus x squared, that is the second multiplication. All right, but we get x to the 4th already. So 1 plus x to the 4th times 1 plus x squared, right? X squared from the first one, x to the 4th from the second one. The third multiplication, that is to the 6th, right? Yeah. So the answer is three multiplications by repeated squaring technique. How about that? How about that? Think about, in order to answer this question correctly, how many pieces of knowledge you need to know? Horner's rule, Pascal's triangle, repeated squaring. You put these 3 pieces together, you get your answer 3. Think about that. Wait, so why is it 3 when the total amount? Yeah, because, all right, that's good question. All right, comment. Yeah, let me repeat his question first. Why is it 3? Yeah, 3 multiplications when the total amount of multiplication 6? Yeah, because he point this, yeah, because the total, the exponent number 6, but we just need 3 multiplication. The reason is we take advantage of the squaring operation. Answer is we take advantage of the squaring operation. Why squaring operation can help us take the, do multiplication faster, because you do the jump way. Yeah, Cormac, every multiplication you do not advance just by 1 number in exponent, you double it. Think about that. You jump fast. All right, the first time you do multiplication, yeah, let's look at this. First multiplication, you get a square, right? The second multiplication, square times square, you jump to 4th power. The third multiplication, you jump to the the longest you can jump, double the 4, you get 8, and so on. The 4th multiplication, you doubling again, you can get to 16 and so on. That's the power of repeated squaring. You jump much faster. You do not jump step by step, single step, all right? You do not do single step. Think about it, you jump double step. Double the previous number of steps. Think about that. You jump in this way, doubling the previous number of steps. How about that? All right, yeah, think about that, yeah. You go up using the stairs. If you do just step by step, then every time you just move one step up. But now every time you jump 2 steps. How about that? 2 by 2. How about 3 by 3? Okay, in that one. But here we do even faster. 2, 4, 8, 16, 32. Extremely fast. That's the power of squaring operation. Right? Yeah, squaring operation. So we can move very fast. How about that? That's the trick. That's the trick. Okay? Yeah. Some smarter way, some smarter idea, you can do much faster, much better. Counting number of times, yeah, right? Yeah. Used, not the actual, right? You get to the point, yeah. What I ask you, actual number of multiplications, right? Yeah. Visually, you see the number of operands, let's say this way, not 1 plus x, you know, this many operands in the formula. So that's what you see. But it's not necessary. We have to use, you know, single 1 plus x factor as the operand each time. Can we use higher degree of the x plus 1 term as the operand? Yes, we can. Nobody stops us in that way, right? It is allowed. You're allowed. It's legal, right? It's legal. Yeah. So we can use that way, the smart way. Yeah. It's legal. Yeah. All right. Okay. So that's pretty much these 2 questions. Yeah. Think about that. Yeah. Yeah. This is just our quiz number 1. From this one, I just give you some idea. In our remaining 5 quizzes, each one you may see 1 or 2 questions as tricky as these 2. You know, yeah, I like to put not very hard. Yeah, we cannot say extremely hard, but a little tricky. Yeah, things like this. Okay. Yeah. All right. Yeah. So I already spent 30 minutes on these 2 questions. Yeah. So let me move to our regular lecture, part B of module 3. Yeah. All right. B.1, reduce problem size by half. Part B, the big title, variable size reduction. Yeah. Here, we apply the idea I mentioned before, that is the problem size reduction approach. To solve a computing problem, there is a big, very useful approach, problem size reduction approach, right? Yes. So in this part, we look at a few examples that in those examples, we will do variable size reduction. All right, so let's look at the first example. Reduce problem size by half. Yeah. Question. Our problem number 8. count binary digits. Now, binary digits, we know that's bits, right? Yeah. You know, the short name for it, bits, count bit, number of bits. Yeah. All right. The question is very simple. Yeah. Given a positive decimal integer n, yeah, find the number of binary digits in its binary representation. Yeah. Short description. All right. Yeah. But to find a solution, you need to do a lot of work. Okay, a lot of work. Yeah, so let's solve this problem carefully. Yeah. All right. The reference on our textbook, yeah, so you can study that. But here, when you look at the textbook, yeah, I check it, the examples I used here in our textbook, the material provided in our textbook, I noticed that the material there, not much, very simple. Yeah. And in my presentation, I add a lot more supplementary material. So you can see in my solutions, in my presentations, you have much more information than what you can find in our textbook. Now, I expand a lot, yeah, because otherwise it is very hard to understand. You know. For this question, that's the case. Yeah. I added much more information in this one. Yeah. All right. Analysis. First, let us review binary representation. Yeah. So this part you learned in Math 3000, discrete math. Yeah. Yeah. Chapter 2, yeah, as I remember, yeah, that's this topic. Yeah, right. For a general integer n, we can write the general representation in this way. Yeah. B coefficients, the bits number, B0, B1 until BS. All right, yeah. But the most significant bit cannot be 0. In order to determine the number of bits we used for n representation, binary representation, we need to make this assumption. B sub s cannot be equal to 0. Yeah. Because we use the bits number, so B sub j can only take 2 of the possible values, 0 or 1, 2 values. If it cannot be 0, then it must be 1, right? Yep. That means B sub s has to be 1. The most significant bit must be 1. Otherwise, we can reduce 1 bit fewer for n binary representation. Okay, all right. So then, if you know B sub s equals 1, and especially you know the subscript s, then you can write out the answer quickly, right? Yeah. The answer is s plus 1. Yeah. Because if you count the number of bits, B0, B1, yeah, because you start from 0, then 1 and 2, all the way through s, you have total s plus 1 numbers. Yeah. The answer is s plus 1. Yeah. That means in order to find the final answer, you need to find the value of s from n. Given n, find that s. That's our initial analysis of this question. Yeah. All right. Yeah. So next step, how to find that s? How to find that s? All right. Yeah. Okay. Yeah. All right. Yeah. Insight. Yeah. Try to find some critical property. Yeah. To discover a critical property. So we need to have the insight. Yeah. So what's that? Yeah. Here we need to do transformation, formula transformation to change the original structure a little bit. Yeah. So here, based on the original structure, look at the, each term, there is a power of 2 structure, each term, power of 2 structure. So we can take advantage of those power of 2 structure. Yeah. So the critical property we explore should be related to that power of 2 structure. Okay. Yeah. How to do the transformation. So here, yeah, one commonly used technique, yeah, division operation. We do division. We do division by 2, both sides of this above in equality. Division by 2. And see, what can we get? Division by 2. All right, yeah. Right-hand side, division by 2, but we need to take floor function because we only want to consider integer result. All right, integer result. Yeah. So we put a floor function there. Yeah. In that way, right-hand side, you can see B0, the first term is gone. All right, because after division by 2, floor function, it is gone. All right, then starting from the second term, there you can see their corresponding power of 2 part, exponent, whose exponent is reduced by 1. Each term, whose corresponding exponent is reduced by 1. Yeah. So that structure, look at that. Okay. So with this new structure, what conclusion can you get? Yeah. In other words, if we want to count the number of binary bits used to represent left-hand side n/2 floor function, how many bits do we have? Right? Yeah. How many bits do we have? Yeah. S bits, right? S1, B1, B2 through BS. So S bits we need, right? You compare the number of bits S here and number of bits S plus 1 before you do the division by 2, the difference is 1. Think about that property. That is the critical property. So we can summarize what we did so far by division by 2 operation. The new number n/2 floor function, the number of binary bits we need to represent that new number is 1 bit fewer. All right, so with that, then, yeah, let me list the observation here. Yeah, okay, yeah. As the summary, yeah. First, the least significant bit is removed after division by 2 operation. Here we're talking about after a division by 2 operation. We have the least significant bit is removed. B0 is gone, right? Yeah. The number of bits is reduced by 1. The number of bits used in the final binary representation is reduced by 1. Yeah. That's our conclusion. Yeah. All right. The problem size is reduced by half. Yeah. What 1/2 of the original problem size, approximately 1/2, right? Flow function. Not exact 1/2, but very close 1/2, right? Yeah. But it's okay. We just treat as 1/2. All right. Yeah. That's the observation. Yeah. All right. Then after that, we should get some formula for it. Yeah. So this kind of reduction, that's the problem size reduction, should give us some useful formula for this whole procedure. So what's that? Yeah. That's a recurrence relation. All right. All right. So here I define a new function, bin rec of n. So that means recursive. That rec represents recursive, binary bits, recursive function. All right. Binary bits computation, recursive function. That means for input n. Okay. Yeah. Bin rec of n equals bin rec of flow function of n over 2, then plus 1. How about that? That's the recurrence relation. That is our final conclusion from our analysis work. Yeah. But we need a base condition. Yeah. For recurrence relation, we always need appropriate base condition. That is bin rec of 1 equals 1. Yeah, yeah. That's trivial. That's trivial. Yeah. After we derive this recurrence relation, then can we find the final answer S in terms of n? That's our goal. Find S in terms of n, our goal. Okay, yeah, all right. Let us solve this recurrence relation first. Yeah. It may not be very easy. You can imagine how to solve it. It may not be easy, right? Yes. Oh, yeah, here. There is one thing I forgot to do from our previous lecture. Yeah, I need to find some time to complete it. Yeah, because it is quite useful. Remember the Tower of Hanoi puzzle problem we solved last time, right? Yeah, but I didn't derive the formula for the number of moves for the n-disk problem. Yeah, I didn't complete that part. That is another recurrence relation problem. Yeah. So I will find some appropriate place, come back to complete that one, because we can learn some useful method thinking in that solution. Yeah. Yeah, because when I look at this question, I recall that one. Yeah. All right. Here, we need to solve this non-trivial recurrence relation. Actually, quite difficult. Look at that. Pretty difficult to solve. The reason is something sticky, not quite comfortable, you know, that is the flow function. Look at that flow function. Do you feel it is easy to handle that flow function? For most people, it is not easy to handle the flow function because it's hard to control, right? It's hard to control. At what time you drop the fractional part, and what time you do not drop the fractional part, right? Hard to predict. Hard to predict, that means there is a lot of uncertainty there. In problem solving, when you have a lot of uncertainty, that would increase the difficulty of the problem. If you can reduce the uncertainty, you can reduce the difficulty level in problem solving. Yeah. Here, we need to find a way to reduce that uncertainty due to that flaw function. That is the first thing we need to do. Okay, all right. Here in computer implementation, internal implementation, n/2, that's just the left shift operation. You move the, a decimal point. Yeah, it's not a decimal, binary point, right? Yeah, because there is, corresponding to the decimal, the row similar to the decimal point, but here we use that binary point. All right, move to the left. Yeah, when you do division, move one position to the left. When you do multiplication, you move that point one position to the right. All right, yeah. So left shift operation in computer internal implementation, so easy, right? You do not need to do some relatively complex operation. Just move that position by one. That's it. How fast it is, right? Extremely fast. Faster than addition. You can think about, for addition, you need to do a lot of work. But move that binary point one position to the left or right. So simple. Yeah. So that one, pretty fast. Yeah. Then the second part, we need to do addition by one. So in this question, addition is our basic operation. Now, every time we need to do one addition. Now, every recursive call, we need to do one addition. All right, yeah. So that is our basic operation. Next, then we want to count the number of additions we need in solving this problem. Okay, number of additions we need. So we use the new notation A of m to represent the number of additions in solving this problem. All right. So then with this function, we can derive a new recurrence relation related to our old one that is similar. A of n equals A of m over 2 floor function plus 1, and the A of 1 equals 1. Yeah. Because we can translate from the left-hand side recurrence relation to the right-hand side recurrence relation easily. Think about that. Yeah, the number of additions we use for Bin rec problem, that's A of n, can be translated to, we need to solve that half size problem. Bin rec of floor function of n over 2, how many additions we need? That is A of the problem size. What is the problem size? Floor function of n over 2. And we need one more addition, right? Plus 1. One more addition. So that's why you plus 1. Yeah. Then A of 1, you just imagine we start from A of 0. That's 0. 0 plus 1 equals 1. All right. So that's the base condition. Yeah. Yeah. Exactly the same structure. The meaning is different. Here we use number of additions meaning. A of n, okay. New recurrence relation, but essentially the same old recurrence relation. Okay, all right, yeah. Next, we need to solve this recurrence problem. Okay, yeah. How to solve it? Now the problem solving. Yeah, the sticky part. how to handle the floor function. Yeah, that's tricky. Yeah, floor function. Yeah, all right. Examine the property here. Yeah. For the floor function, the value of n/2 floor function equals, based on n even or odd. When n is even, it is n/2. When n is odd, it equals n-1 parenthesis over 2. Yeah, that's simple. Yeah. All right. Although it's simple, yeah, but the question is, in these two cases, n even and n odd, these two cases, which one is easier for us? Yeah, because we as problem solvers, when we solve a relatively hard problem, we like to look at a relatively easier case first. Yeah, as a natural thinking, natural way, we like to select relatively easier case first. Do you think that even case easier or odd case easier here? All right? Yeah. Yeah. I believe most people will select even case. Right? Yeah. Yeah, definitely so simple. Yeah. Right. Easier case first. That means when n is an easy even number, yeah, we can simplify our original equation, right? Yeah. Or when n is even, we can remove that floor function, you know, by reducing the uncertainty. How about that? Yeah. Okay. All right. So here, the next question I want to ask, what do we wish to have? Yeah. Because when you make your wish, you always try to find the best way for you, right? You won't select the hardest way, right? When people ask you make your wish, for most people, they select the most comfortable way, right? You won't select the most difficult way, right? Yeah. Here, the most comfortable way for us, yeah, we select n is even. How about that? In the first round, yeah, from our current recurrence relation, the first round, we make our wish. Our wish is n is even. How about that? Okay, you're allowed to make your wish. Okay, here, you're allowed to do that. Yeah. So we want to make this question as easy as possible. All right. But that's the first round wish. Not done yet. We need to make our second round wish. All right. The second round, we start from left-hand side, a of floor function of n/2. The right-hand side, we have floor function of n/4. When you are allowed to make your wish, what kind of wish you like to make? Okay, yeah, yeah. Make it as easy as possible for you. Okay, yeah. How about n/2 is an integer? How about that? N is multiple of 4. How about that? Okay, or n/2 is even. How about that? If you're allowed to do that, you may wonder, how can you make that kind of assumption? Yeah. Later you will see, yeah. Later you will see, yeah. We have freedom to choose to do that. That's our freedom, all right? Yeah. So n/2 is even this time, yeah. Then the next round, all the way down to the bottom, if you can keep making your wishes like that, eventually you will have the situation, n is power of 2. If you can assume n is power of 2. That will make your life easier. How about that? Make your life easier on this particular question. How about that? Okay. All right. So let's move to the next slide. This time, when we try to solve this recurrence relation problem, we make a strong assumption. What's that strong? N equals power of 2. 2 to the kth power. How about that? Because that corresponds to the most friendly form we could have for this recurrence relation equation. Recurrence equation. Most friendly form. Think about that. All right. All right. So let's try to get into the equation. Yeah. This time k equals log base 2 of n. Yeah. All right. So we can write our new recurrence relation. Yeah. It's like that. Okay. A of 2 to the kth power, left-hand side, equals A of 2 to the k minus 1 power and a plus 1 with base condition. Now, in this one, you can see the floor function is gone. How good it is. We do not have to deal with the floor function in our new recurrence relation. That's nice. Okay. That's the freedom after we choose some special assumption, the freedom we enjoy, finally we get this very friendly form for the recurrence relation. How about that? It is very special. I agree. It is very special. Don't worry. We have the freedom to work on special case first. Okay. Later, remember, we will bridge the gap. There is a gap bridging step. How about that? Later, we will bridge the gap. There is a gap. We know there is some pretty big gap we need to bridge. But let us, do some friendly form work first. All right. Let's continue the work we need to do. The first recurrence relation equation we write like this. The second one, reduce the exponent by 1 in each term, like that, the second line, and so on. Okay? Keep doing in this way until we reach the bottom equation. Now, can we add all these equalities up and do some cancellation for simplification? Yes, let's do it. First round cancellation like that, when you add up both sides of all these equalities. Next round, and so on, this kind of diagonal cancellation. How about that? Yeah. The last one, cancellation like that. Okay. Then we add up all the remaining terms for both sides. The left-hand side, A of 2 to the kth power. The right-hand side, you count the number of ones you have. Can you keep track of how many ones you have? How many lines do you have? Look at that. How many lines do you have? Yeah. Use the counting by reference method. Counting by reference method. Okay, counting by reference method. All right. The first line, use the reference number k. How about that? The second line, use the reference number k minus 1, and so on. All right. The last line, use the reference number 1. When you count from 1, 2 through k, you have k lines. How about that? K lines. But this A of 2 to the 0 that is another one, all right, by the base condition. So you have k plus 1. That is the answer. That is the answer. Yeah. But this answer we just derived still in terms of k, not in terms of the original variable m. So that's not good enough. We need to go back to the original n variable. Okay, yeah, all right. So now the result, yeah, we go back to the original, yeah, representation, recover, yeah, 2 to the k, that is a of n, then 1 plus k, we already have its expression, log base 2 of n. So our final answer representation, but remember, this is for special case, n equals power of 2 special case, not the general case, okay? Not the general case, yeah, yeah. All right, so the next step, our goal is solve this problem for general case, right? Yeah, that's our goal, yeah. But how to bridge that gap? That gap is pretty big, right? From this power of 2 special case to the general n case. That gap is too big for us to overcome, right? But we have to overcome that step. Yeah. All right. So the question, how to advance to that step? All right. Yep. How to make that critical step. Okay. Yeah. Remember, we learned a strategy before. So here we have another problem-solving issue here. So we need to apply another effective strategy. That's guess and verify. Remember that? Guess and verify strategy. Okay, guess and verify strategy here. All right. When we move from power of 2 case to the general case, can we make a guess first? Make our guess. Because the guess, we only want to approximate the final true solution the best we can. All right, yeah, the guess. We're allowed to make some small error, but we will adjust it after we find the error. All right, but a good guess is very helpful. A good guess is very helpful to get this problem solved. So the next step, we need to make a good guess here. Yeah, how to do that? Yeah. For the general case, let us guess. Yeah. Guess we are not making our guess from nowhere. We have a lot of useful information to get started. Okay, to get started. Yeah, look at this formula. With this formula, can we make a good guess? All right, yeah, so let us make the good guess. Yeah. All right, here, because this term log base 2 of n for the general n may not be an integer, right? If it is an integer, the easiest, the fastest way to make it integer, there are 2 options. Ceiling function, we replace log base 2 of n by either ceiling function or floor function. There are 2 possible ways we can make that non-integer expression to integer expression. How about that? Okay, yeah. All right, so there are 2 options, but which one is a better guess. We have two options. Yeah. It cannot be both correct, right? One must be false. One must be false. We should eliminate the false one. How about that? Yeah. We should eliminate the incorrect one. Okay. Yeah. How do you know which one is incorrect? Okay. Yeah. Do experiments. Yeah. The fast way is just do some simple experiments. Okay. Yeah. All right. To eliminate one of the two options. So how to do that? Yeah. Let us consider n equals 3. All right. First, we can find the answer for n equals to 3, the answer quickly, right? Yeah. Because we know 3, if we write a binary representation, that is 1, 1, right? We know that. 1, 1. Yeah. In binary representation, yeah, usually we do parentheses sub 2. Yeah. Binary representation, 3 equals parentheses 1, 1 sub 2. Okay. All right. So then the number of bits we need, that's 2. The answer is 2. Okay. Yeah. All right. Then when we get to the expression, which one gives us 2, then we will take it. All right. Yeah. All right. So 1 plus floor function log base 2 of 3. What do we get? 3, we know 3 greater than 2, less than 4, right? Yeah. If it's 2, log base 2, we get a 1. If it's 4, log base 2, we get 2. So 3 is something between 1 point something, right? 1 point something, you take the floor function, that's 1. So that gives us 2, right? Yeah, yeah, this one looks good. But if you look at the second one, seeding function log base 2 of 3 seeding function, you will get 1 plus log base 2 of 3, that's 1 point something. Seeding function, that will be 2. 1 plus 2, you will get 3. 3 now equal to 2, right? We know the answer is 2. So that means the option seeding function is wrong. We should drop it. Yeah. That means if we want to make the best guess we can have, it should be 1 plus floor function of log base 2 of n. How about that? That is the guess part. Yeah. Here we apply the guess and verify strategy. That is the guess part. But not done yet. You just make a good guess. The guess is the closest we can make, right? But you haven't verified it. You need to do that verify step, okay? To do verify step, you need to do it, okay? Yeah, yeah. We will leave that part, later, yeah. But yeah, here, yeah, I spent too much time on this question. I didn't expect to make such a long time today, so that will drag down our, our progress quite a lot, because our part 1 already we spent 2 class sessions. This part 2 looks like, another 2. Yeah, so that's too much for us. Yeah. So although we can adjust, still we have a lot of room to make adjustment. Yeah, but at some time I need to speed up a little bit. Yeah, I need to make adjustment a little bit. Yeah. All right. Yeah. So for today, we just stop here. And so let's look at the, the assignment timeline. Right now, you're working on quiz number 2 and the project number 2. Yeah. And next week, I will assign your homework number 1 next week. Yeah. And also next week, quiz number 3. Yeah, because next week we will complete module 3. So next week we will have 2 new assignments. Yeah. But this week we won't have. Yeah, we won't have new assignment. Yeah. All right. So that's it. So let us stop right here. Yeah. But I will try to adjust the remaining materials, try to catch up our original plan. All right. Yeah. So that's it. Yeah.